actually covered a little bit of that before we covered chapter IA, didn't we? I got ahead of myself there. So this is where we were last time. Remember that we were actually starting to talk about VSEPR. Okay, so we were actually talking about VSEPR, and we had finished just talking about Lewis structures. Okay, so this is actually what the VSEPR structures look like for these various different ones. Notice this is tetrahedral. And so this one right here has how many electron groups? 4. How many ones have atoms at the end? 4. Yeah. And so this one right here, it's electron geometry and molecular geometry are the exact same, which is tetrahedral. You know that because you have 4 electron groups. Okay. Now, if we go up here, we have 3 electron groups around this one. Remember that any bond is going to be an electron group. Okay. Single, double, triple bonds are all 1 electron group each. Okay. And then a lone pair is another electron group, but doesn't count in terms of molecular groups, right? Okay, so this one right here, this is trigonal planar for the electron geometry, okay? This one over here, what would the electron geometry be? Tetrahedral, yes. The electron geometry of this one here is tetrahedral, same as this one down here, okay? What would be the molecular geometry? Trigonal pyramidal, exactly. So this electrons up here, they are taking up space. They are causing that to be that shape, right? But when you're talking about molecular structure, all you care about is the atoms, okay? And that's the shape you're documenting. Okay, so this one right here, this is linear. It has 2 electron geometry, right? This one's 3. The electron geometry would be what? Trigonal planar right there, right? The molecular geometry, on the other hand, would be bent. You got it. This one here, the electron geometry is tetrahedral again. Perfect. And then the molecular geometry, that's bent. Yeah. That's water, by the way, in case anybody's curious. That's what the shape of water is, bent.
What do you say about like double and triple bonds?
They're 1 electron group. So let's say this was like a double bond right here. It doesn't matter. That's 1 electron group. You end up with the same sort of thing. Okay, and so this is some different examples here. For example, here we have a triple bond right here. And so this is 1 electron group there. This is another electron group, which is the single bond. So around this right here, this is going to be linear. Can everybody see it okay? By the way, triple bonds, typically everything's linear because it's basically impossible to do anything else. Okay? Like if it's a carbon, you have a triple bond, you only have 1 other bond, right? So it can only be linear. If it's nitrogen, you have a lone pair. So you have a lone pair and a triple bond, 2 linear again, aren't you? So if you have a triple bond, you pretty much know it's going to be linear. Yeah. It almost becomes impossible to be anything else, though you can get other structures if you go to things like sulfur down in periods 3 and 4 that have extra octets. Okay? That's the only place you can get that sort of weird stuff. Okay. This right here is propanone. This is a ketone right here. And so what you'll see is this has a double bond here, single bond, single bond. That's how many groups? How many domains? 3. 3 domains. So the electron geometry, trigonal planar, molecular geometry, exact same, right? Because we don't have any lone pairs. So, this one right here again, tetrahedral. And so we have tetrahedral on both sides if you look at that. And everybody say okay? By the way, that's why the zigzag pattern. You realize that, right? If we just take out the hydrogens, what are all these structures? Well, they're tetrahedral, right? If we take out 2 of the groups, they're always bent. And so they are always bent. That's why the zigzag is. It's literally the tetrahedral structures over and over and over, right? Yeah. We're just documenting that. I know everything had a reason. And so here we actually see the summary of that. Notice that again, we have these tetrahedral structures over and over, right? And so the structure looks, it's tetrahedral here. There's a lone pair taking up space. It's tetrahedral again here. There's the hydrogens, right? Tetrahedral again. And then we again have a tetrahedral, two lone pairs taking up the space. And so bent, bent, bent. Rubber bent.
Okay. Is it not hydrogens connected to them though?
Huh?
I thought like anytime you have a carbon, you assume that like you have two hydrogens.
Yeah, there's two hydrogens on each of these carbons. This is an oxygen, this is a nitrogen.
Oh.
Yeah. And so this nitrogen here has a lone pair, and this oxygen here has two lone pairs. Yeah. And those are right there. Yeah. The black, by the way, in any of these things, that's carbon. Red is typically oxygen in models. This is how models are colored too. Blue is nitrogens. That's actually because the blue from ammonia, many ammonia compounds will actually turn a blue color. So if you ever look at those. And then the white little dots, the really small ones, those are hydrogens. So whenever you're looking at these things. If you get a model kit, it'll be the same sort of thing. I highly recommend it to get a model kit. Let me re-stress that. If you need to borrow a model kit, there are ones in there just not as nice as the one that I recommended to you, and they take up a lot more space. All right. Okay, so let's talk a bit about ions. So the rules apply equally well to ions. You just have to remember that you're going to be losing or gaining electrons. Okay, so you can end up with not having 4 electron domains around these things. Okay. For example, we have CH3 here plus. That's going to be a cation. It's called carbocation. This is going to have a trigonal planar geometry because you literally can only have 3 groups around it, right? The other group just doesn't have any electrons go in it, does it? So there's nothing. The CH3 minus, this is the anion, so carbanion. This is going to end up with an electron geometry where it has a lone pair. And so that's going to be an electron geometry that's tetrahedral. And the molecular geometry is going to be trigonal pyramidal, like so. Kind of like a amine would be, right? Kind of like a nitrogen. Okay? It just has a negative charge. Anybody have any questions about that so far? Okay, so those structures actually become very important later. So make sure that you understand those to some degree. For example, this one right here, yes, it doesn't have any electrons in it, but this is a free p orbital up here. Okay? It's a p orbital, it's just empty. And this thing has a positive charge. What do you think happens if any electrons come near that? Yeah, it's going to just snap right onto those, right? And they're going to be attracted, pull into a bond. So these things will actually build up and we'll actually use them in a little bit here. Okay. All right. So this right here is dash wedge notation. It's very, very similar to line angle notation that we used before. The difference is we're going to add dashes and wedges so we can denote 3-dimensional structure. Okay. Anybody ever drawn in 3-dimensional structure? And you do like the angles right and you fade it. Okay. And when it's coming out towards you, you fade it dark, right? When it's coming out away from you, it fades away and hatching, right? So it has less coloring in it. Okay. Same thing here. So a straight line, this is going to represent the bond that lies in the plane of the page. So if you see a straight line, then that one actually represents a bond that's straight in the page. Okay? Okay, it's not coming out towards you. It's not going away from you. It's flat. All right. The ones that are wedges are going to be coming out towards you. And so see how this is that colored in dark wedge? It's coming straight out towards you and trying to hit you. Okay? It's three-dimensionally jutting out away from the page. Okay. Again, towards you. So, okay. The dash is fading away from you. So it's past the plane of the paper, past the plane of the screen, going away from you. Is that making sense? Okay. So what this looks like, I'm going to use my hands. If you ever need to represent these structures, you can easily use your hands, okay? And oftentimes they're going to help you so you understand betterly where things are three-dimensionally, right? So I have hydrogens like this. Can everybody see that's in the plane, right? And then I have hydrogens that are coming down like that. And that's that tetrahedral structure, isn't it? You can try it yourself if you want. The other way you can do it is, you know how people used to go like that? Like that. It's the same structure. Yeah, I know. It's kind of a gang symbol-ish. All right. Notice that we can actually rotate this. If we rotated it, we can change the line, the wedge dash notation. So we'd have two coming out towards you, right, and two coming out away from you. Notice that's the exact same structure, isn't it? See that? We're just rotating that in space. Okay. Can everybody sort of see those now? They are, but this one's a lot harder to write. So you'll never see that written out by anybody who knows what they're doing, because it's just a lot more work, right? But they're entirely correct forms. If you're trying to emphasize away and towards you, you can write it out like that. Okay? Nothing wrong with that. It is correct. Okay, so let's look a bit more on the tetrahedral geometry viewed as perpendicular versus... so right here, we actually have this butane with an alcohol coming off of it. And so we represent these carbons as all being in one plane. And so that form of a ring is flat in that plane. And then what we do is we represent that oxygen as coming out towards us. Can everybody see that okay? Okay. All right, so note that the two bonds that make a V in the plane of the page will open in one direction, whereas the other ones are going to open in a perpendicular direction to that, right? And so you always have two V structures that are in perpendicular directions whenever you're looking at tetrahedral geometry. Okay? All right, so how can we view this molecule from a different perspective? So in this case, we have a desired operation, which we're going to rotate this 180 degrees. What is that going to look like? Does anybody have their modeling kit? Nobody? Whoa, I am super disappointed. No, I really kind of am. Okay, so I did tell you Linus Pauling said you can't understand this without modeling kits, right? The guy that came up with the structure for DNA without actually having anything to tell him what it looked like. Double Nobel Prize winner. Linus Pauling is going to be appalled by you people. From beyond the grave, of course, because he's been dead for a bit. But okay. All right. Highly recommend you grab some modeling kits. They will make your lives easier learning this stuff. Okay. Okay. So one of the ways you could do this, you can construct a model, of course, using a modeling kit. It looks like this. Okay. And see how the oxygen is coming out towards you in the model. Chlorine coming out towards you in the model. Chlorine up here going away from you. Everybody see that okay? Okay. So if you flip this, what is this going to look like? You got it. You got it. So this is going to go down here, right? And then it's going to come out towards you. Perfect. Yeah. And all the rest of them are going to flip the opposite directions. And so it looks like this. And you got it. That chlorine up here on the bottom coming out towards you now, right? away, and away. Okay. So, what if we redraw that? Well, how do we redraw now? We put the pointy end facing down, don't we? Okay. And all the other ones are just going to flip from being wedge. If they were wedged before, they're going to be dashed, right? If they're dashed, then they're going to be wedged. Okay. And so you're going to just flip dash versus wedge. Right. Everybody have that okay? Okay. All right. And your modeling equipment on your homework, you can actually use that to play around a little bit. You can actually rotate things, and it will help you sort of absorb what these look like three-dimensionally. Okay? Not as well as a kit. A kit would be easier. But really, like, keep in mind, you can hands-on play with these things. Like, that's an unusual thing, right? And people learn better when they're hands-on playing with them. So, because it's how you literally learn to learn when you're a baby, right? So, okay. The polar covalent bond, this is going to occur when atoms have different electronegativities are bonded together. Let me point a little something out real quick about learning, by the way. Did you guys know that you learn better if you learn multisensory? And especially if you can engage with it in the same way you would as a baby, which is your hands. Those are the things you actually learn the best. It's one of the reasons why if you write, you actually learn better than just listening and hearing and thinking. And you learn better with actually writing on paper than you learn from typing, because it's a more direct pathway. And so, like, actually playing with these things with your hands is actually a big improvement in your learning. Like sitting there and literally using your hands. If you don't have models with you, use your actual hands to represent it. Okay? Like, you can represent these structures using your hands, right? Okay. That is bond, right? And you'll actually absorb tremendously more, not a little, a lot more. Okay? Because that's how our brains are wired, right? As being humans. Okay. If you can then engage your smell on top of everything else and your various different senses, you'll gain even more. Okay? Smell is kind of a hard one to do, though. So I guess we'll get smells in the lab, right? Yeah, there you go. Polar covalent bond. This is going to occur when atoms have different electronegativities. They're bonded together. If you have the same electronegativities or very, very close, they're going to be referred to as a covalent bond. Okay. When you have, so these right here are called bond dipoles. See these little arrows right here? Okay. We have the black arrows right there. Those are bond dipoles. And so when we look at HF, hydrogen is much less electronegative than fluorine, right? And so fluorine pulls all the electrons towards it. And what we end up with is a positive charge on hydrogen's end, negative charge on fluorine's end, right? In this case, we have a single bond dipole. And so we end up with a molecular dipole. That's the red arrow, which is the same as the bond dipole, right? Okay. And that was going to be what is our net molecular dipole. What does dipole mean, by the way? Di meaning two, poles. Yeah, exactly. So literally a magnet, right? Positive one end, negative the other. There you go. Okay, this is carbon dioxide right here. And so what we see is we have two bond dipoles. They're pulling in opposite directions equally. Everybody see okay? Okay. And so this one right here, the net dipole is 0 because it cancels out overall. We don't have any overall dipoles. But oxygens are negative, carbon is positive, oxygen over here is negative. Okay? So it does have bond dipoles, but not a net molecular dipole. Okay? These are the units, by the way. They're called debye's. That's that D right there. And how exactly you calculate them is a little more complicated, but it's essentially the difference in electronegativities. Okay? When you have multiple ones that have to add together, then you're going to use vectors to do that because their directionality matters. Okay? But you can kind of get a sense of them if you think of like people pulling, right? at each of the ends. Okay, now this right here is what you probably remember as a nonpolar compound, right? And that's because, well, it has no overall poles for the compound, right? Okay. In terms of bonds, though, these are polar covalent bonds, okay? Because the bonds have poles, right? Just not the compound. Okay, this right here is water. It's going to have both. So the bonds have poles. You can see those right here. Hydrogen's positive, oxygen's negative, right? And while they do cancel a little bit this way, they add together in this direction, right? And so your overall molecule has a dipole, and it's facing this direction. The hydrogen end is positive, the oxygen end is negative. And so you get a net dipole that's 1.8. Fairly strong. Okay. Anybody have any questions there? Okay. This is some more examples. Again, notice that vector addition is happening here. So you can cancel out, like, let's say if you have chlorines on every side of it, we cancel out, so we have no overall dipole, right? Again, our bonds have dipole, but the overall molecule does not. Okay. This one right here doesn't fully cancel out. And so what we see is the hydrogen end has quite a bit of a dipole, or has quite a bit positive charge. Chlorine end has quite a bit of negative charge. Okay. Does everybody see it okay? Okay. All right. So our different functional groups in a compound, these can lead to very different physical properties. This is actually a table that sort of sums these things up, and we sort of are looking at what these sort of physical properties will be. Now, notice that the molar mass is usually most useful in determining things like what the sort of boiling points would normally be. So if you have a higher molar mass, then your boiling point typically goes up, right? Okay. And that's because of London dispersion forces. Do you guys remember those? Okay. Now, this one right here, this is actually ionic. So technically it doesn't have a molar mass. It would have a formula weight because this is actually an ion-ion molecular forces. Excuse me. All right. And so what we see here is the boiling point and melting points for this are very high compared to the others because those are ionic forces that you have to break to actually get them to boil or melt in this case. The solubility in water is pretty good because it is ionic. This is the dipole, magnitude of the net dipole. There actually is not much of a net dipole on this. It's not really usually counted because it actually is just straight on charged, right? It has positive and negative charges to it, okay? Again, this one right here, this can do hydrogen bonding. This is methanoic acid, often called formic acid. It's that grass scent if you ever crush like Asian beetles. This is a molar mass. It's very similar to this one. We're actually using that to compare, by the way. And what you'll see here is this has more hydrogen bonding it can do. And so it has a higher boiling point than ethanol. Okay. And so this right here is a carboxylic acid. That's the functional group. Okay. And so the solubility here, they're called infinite in this book. Usually they're called miscible, meaning you can combine any amount. Okay. You could make a 50-50 solution if you wanted. All right. Here's melting points. Anybody have any questions about that so far? No. Okay, here's some more examples of physical properties for the different functional groups. And what you'll notice here is as we get up here, ethanol right here can no longer form hydrogen bonds with itself because it doesn't have a hydrogen bond donor, meaning the hydrogen part of the hydrogen bond. Okay? And that means it can only do dipole-dipole interactions. And what do you notice about the boiling and melting points? They went down a lot, didn't they? Yeah. And so that's dipole-dipole interactions that you're seeing there. This has less dipole-dipole interaction because it has less magnitude of the dipole right there. This one right here is propene. That's the double bond. Propane and then ethane. Notice as we go here, these are very similar for melting and boiling points because all you have to depend on here is what's called induced dipole, which you know as London dispersion forces probably. Okay. Did you ever hear of it as induced dipole, Yeah, no. Yeah? Really? Were your textbook from last semester or
I think it was, I think from class.
really? Huh. Yep. Most general chemistry textbooks do not use that terminology. That's actually quite unusual. So that's kind of interesting. Anyways, yeah, same thing. Everybody remembers what that is, right? Okay, it's literally probability of your electrons not being on the same side. Okay, so the last one you see here, this actually has less molecular weight. See that? And so it just has less London dispersion forces. And so your boiling and melting points both go down. Right? That's what that one is. Okay, and so let's talk about the types of intermolecular forces. We have the ion-ion interactions. We have the dipole-dipole interactions, hydrogen bonding. Is there any actual real difference between dipole-dipole and hydrogen bonding? Yeah, there's stronger ones, but what it really is it's more of a combination of effects that just make them much better dipole-dipole interactions. And so when we're looking at dipole-dipole interactions versus hydrogen bonding, it is, yeah. Exactly. Yeah, and hydrogen bondings have very special parts to them that let you really concentrate those dipole-dipole interactions. Okay. Mostly that being that charge concentration and very short bond between the hydrogen and the oxygen, nitrogen, fluorine, etc. So induced dipole versus induced dipole, often called London dispersion forces. And then we have ion dipole interactions. This is actually in order of, it's actually out of order in terms of strength. What is the weakest one? London dispersion. Yep. That is the weakest one individually. Okay. Which of these oftentimes gets the strongest, by the way? Ooh, we have some disagreements. So ion is typically very, very strong. Okay. However, interestingly enough, London dispersion forces can actually get the strongest of any of these in some cases. That's because London dispersion forces happen all the time everywhere. Literally, if you have two molecules together, I don't care what they are, you have London dispersion force, okay? If you have a big enough molecular weight, those London dispersion forces can get huge. And that's why, for example, you can have things like asphalt and stuff that are actually need very high temperatures to melt, okay? Engine oil is London dispersion forces. And so they can get pretty high, though you are right that ion-ion forces are the highest ones that we can find. I don't know of any London dispersion forces that eclipse the highest ionic force ones. Okay. So in terms of individual, it would be the correct order. So the correct order would be ion-ion interactions. Then ion-ion would be the highest energy to break. Okay, so they'd require the highest temperatures to break. The next one would be ion dipole. Then it would be hydrogen bonding for individual ones. Okay, again. Then after that would be dipole-dipole. And then it would be induced dipole, or London dispersion forces. Okay. And again, that would be individually what they are. Keep in mind, if you add up like 10 hydrogen bondings, hydrogen bonding can get really strong. Okay. If you put 1 million London dispersion forces together, they can get very strong, right? Okay. By the way, can you ever not have London dispersion forces? As long as you have electrons around nuclei, you have London dispersion forces. Okay? Anybody know what the London dispersion forces actually are? What causes them? Kind of. It's probability. Okay? So let's say we have equal road lengths. Every time you guys come in, there's a probability that more people end up on this side than that side, right? Every time that happens, you guys have created a induced dipole attitude because you've created a negative versus positive zone. Okay? And anything next to it, the negative zone is going to repel the other electrons. The positive zone would then attract those, right? And it'll induce another dipole that will then fluctuate slightly together for a little while and then break apart due to probability again. Okay? Okay, so that's just a pure probability. It has to happen just by the fact there are electrons around nucleus. All right. So melting points, boiling points, and intermolecular interactions. As we maximize our interactions, what are we going to get? A solid, right? So solids are going to be where you maximize those interactions. As you break those solids up, you're going to undergo the process of melting. Okay? Once you've broken up typically about 20% or so of those interactions, that's going to be where you form liquid. And that's going to be where we usually call ourselves melted. And so what we have in the terms of liquid is we have broken up usually about 20% or so of the interactions. You still are mostly interacting and have mostly intermolecular interactions happening. But you've broken enough that they can flip over and over and move. And that's what you consider flowing, right? Okay. Once we boil something, we've blasted almost all the interactions apart, though you can still have a few here and there. But typically when we think of boiling, we have destroyed all the interactions. All the particles are bouncing everywhere, all over our container, and they don't have time to really interact with each other much. Okay? When they don't interact at all, that's considered our ideal gas, and that's where you use like the ideal gas law and stuff. Okay. All right. So this right here is ion-ion interactions. You notice we have a positive, we have a negative. They're attracted together, and that's an ion-ion interaction. That's actually what you call ionic bonding, by the way. So that is ionic bonding as well. You'll notice that technically this is not an intramolecular force. An intermolecular force, excuse me. This is an intramolecular force, okay? Because we typically classify this alongside covalent bonds, right? Ionic bonding, covalent bonding, okay? So ionic bonding is kind of interesting because it actually bridges that gap a little bit, okay? All right, so again, ion-ion interactions, these are considered the strongest of the intermolecular interactions because you're getting to the point where realistically, you're almost at an intramolecular interaction. You're almost having to break bonds to do this, right? To separate these. Okay, so dipole-dipole interactions. So these are going to be where you have a net dipole and it's attracting another net dipole. And so you have the negative charge here that's partially negative charged. It's going to attract to another partially positive charge. Okay, and they'll literally line up like little magnets. Like you have your Legos and they have the magnet pieces and they all get clumped together. Okay, and that's your dipole-dipole interactions. All other factors being equal, the strength of your dipole-dipole interactions will increase as the magnitude of your dipole increases. Okay, so the larger that magnitude of dipole, the stronger the magnets, the better, stronger these attractions will be. Which compound has the higher melting point between these two options? Yeah, the sodium's going to be ion, right? And so you'd expect the sodium, all other things being equal, to be your higher melting point. Okay. What is this one, by the way? That's a dipole, isn't it? Yeah, it's going to be a dipole one because you have this double bond oxygen, right? So how do I know this one's going to be ionic, by the way? Ion, an ionic compound. Yeah, metal, right? Metals almost always mean that's ionic, especially if it's something electronegative next to it, right? Okay. Now, note that we will have in this semester cases where metals will actually form covalent bonds. Okay. And so that's going to show up. What actually creates something to be ionic? It's the difference in electronegativities, right? So it's how different those electronegativities are. Typically, 0.4 is considered the cutoff between polar covalent and just covalent. And as we get significantly more than that, we start getting up to like 0.8 and 1. We're going to be ionic, right? Okay.
How did you know that other one was dipole?
There's a double bond oxygen, so it can't be even across. Yeah. This oxygen here could not have had it even across it. Like it couldn't be carbon, oxygen, carbon. And so the fact that that oxygen is asymmetric uneven means there's a carbon-oxygen bond that has a dipole. Yeah. Okay. All right. Let's talk about hydrogen bonding now. Now, hydrogen bonding's a very unique case of dipole-dipole interactions. Okay. It is so unique that it does kind of need its own category because it's incredibly important too, especially for us. Like all the things about us living require hydrogen bonding. We've never detected life without water. So, yeah. Now, again, the dipole-dipole interactions do not account for some of the highest boiling and melting points among these uncharged compounds. So we actually group those into hydrogen bonding. This is going to happen when we have a hydrogen bond donor and a hydrogen bond acceptor. So this right here is called donor, DO. Okay. This has to be a nitrogen, oxygen, or fluorine. Those are typically the only ones that will be electronegative enough and have a lone pair to be a hydrogen bond donor. Okay. So the two important parts here is this has to be electronegative enough that pulls almost all the electronegativity away from the hydrogen. Okay. So it has to be highly polar covalent. Can't be ionic. It has to be highly polar covalent. The other important part about this is these all have lone pairs. You have to have at least one lone pair, okay? Because that's where you're going to concentrate that negative charge so you can get overlap. Is that making sense so far? Okay. Note that even if you had something incredibly electronegative and it didn't have any lone pairs, it would not be able to be a hydrogen bond donor, okay? Because you can't have the overlap. This one here is going to be a hydrogen bond acceptor. Did I say donor here? Yeah, that's the acceptor portion. 1 second. Yeah, I wasn't actually watching where I was pointing. Okay, rewind. Okay. All right. So the hydrogen bond donor is going to be actually referring to the hydrogen right here. It's still important to have something very electronegative here because it has to pull almost all the electron density away from your hydrogen. And so you're going to get a partial positive charge on the hydrogen. Hydrogen is the only one that will do this because it has to be small enough and a small enough bond here that it can reach in and overlap very strongly. Okay. And so what you'll notice is that hydrogen here is the only one that does that because it's very tiny, right? Yeah. Because it doesn't have extra space in those orbitals, right? Okay. It's energy level 1. Okay. And so you have the hydrogen here. It has to be off of nitrogen, oxygen, or fluorine. Now, this actually, there is an expanded set of hydrogen bonding, but we won't use it in organic chemistry, okay? We'll never talk about that in organic chemistry. It just doesn't exist for us. Okay. But if you ever want to go further, we can talk about that. Okay. You can actually make hydrogen bonds in some interesting ways. Okay. So this right here is the hydrogen bond donor. Literally donates a hydrogen to the bond. All right. This one here is going to be the hydrogen bond acceptor. This is where it's important to do the lone pair. Okay. And again, you have to have nitrogen, oxygen, or fluorine because it has to be electronegative enough that it actually can pull that electron density, that can keep that electron density pooled in one spot. Okay. And so what you have here is a very electron rich lone pair that overlaps with a very electron poor hydrogen and creates something that is not quite a covalent bond level, not quite ionic bond level, but starts approaching it in strength. Okay. Very strong one. Very strong overlap. Is everybody okay with that so far? Let me note here that an interesting thing about hydrogen bonding, is that they have a tendency to trade hydrogens here. So when you form hydrogen bonds, it's not unusual here for this hydrogen to be ripped off onto this acceptor here, and for your donor here to actually lose the hydrogen. Okay, that happens fairly often, and you know that as like acid-base reactions, right? That's actually what that is. So when you have like a, let's look at the liquid water up here. When you add acid to liquid water, anybody know what actually happens? Okay, you probably think you add the acid and then the H plus like leaps around and moves around here. It's not what happens. When you add the H plus, it actually adds to one of these over here, and then this one loses the hydrogen here. And then this one loses the hydrogen here, and so on and so forth. So technically the speed that this can happen actually can approach the speed of light. You didn't know that, did you? So when you acidify a solution, theoretically, in reality, it goes much slower than the speed of light. But theoretically, it can approach the speed of light, the speed of information exchange. Okay? Pretty wild, huh? Nobody ever thought about that? I'm a little saddened. Okay. So anyways, nitrogen, oxygen, fluorine with hydrogen bonding. That's how you know hydrogen bonding is going to occur. You need a donor and acceptor. Could we have a compound that is a donor only? Yeah, we can. Could we have a compound that's an acceptor only? Most definitely. For example, right here, we have a example of a acceptor only. So this one is donating this hydrogen bond right here. That's the hydrogen bond donor, right? This one right here is the acceptor. Okay. And it can't itself donate a hydrogen bond from that oxygen there, can it? Because there's no hydrogen. Okay. This one is kind of a misnomer. That's not how that hydrogen bonding actually occurs, by the way. They actually pair up as a pair. And so this hydrogen bond should be hydrogen bonded to that. For some reason, your book used this example, and it's kind of wrong. But yeah, this one makes a pair. Okay. And so you directly just double its molecular weight when you're looking at boiling points. But anyways, it still demonstrates hydrogen bonding pretty well. And so this is how you hydrogen bond. Typically, it makes like a network of hydrogen bonding. That network is loosely hexagonal shaped. And so has anybody ever made snowflakes and then cut them? You make like little hexagonal cuts in them. Yeah. And if you ever look at crystal structures for like snowflakes and actual snowflakes under microscopes, you know, they're like hexagonal shaped. It's the hydrogen bonding that's making the shape. Ooh, so cool. So pretty. It is pretty, by the way. All right, so this is ethanol. Notice again, this has a potential hydrogen bond acceptor right there, potential hydrogen bond donor. And in fact, this one can take two hydrogen bond accepting. So it can accept two hydrogen bonds, but it can only make one. Okay? Because it has two lone pairs.
Why is that an acceptor? It's just because it's oxygen.
Oxygen with a lone pair. Yep. So oxygen with a lone pair, nitrogen with a lone pair, fluorine with a lone pair. Those are acceptors. Donor is the hydrogen is bonded to the oxygen. Yeah, as long as you have a hydrogen on the oxygen, donor, or nitrogen or fluorine, of course. This right here is methanoic acid. It's carboxylic acid right here. Notice again, we have the potential hydrogen bond acceptors, both of these oxygens, but only one donor right here. Okay. All right. This right here is talking about the strength of your hydrogen bonds. So oxygen is a bit more electronegative than nitrogen. And so typically your hydrogen bond for oxygen and oxygen hydrogens are going to be stronger. Nitrogen, on the other hand, typically makes a little bit weaker of a hydrogen bond. And we can actually see this in the case of ethanol and ethylene amine. And you can see that difference. It's a pretty significant difference, actually. Yeah. Though part of that is actually because there's only one acceptor on this nitrogen here, versus this one has two acceptors, so you can make networks. Whereas this can't make networks, really. Okay. And so this one's induced London dispersion forces, induced dipole interactions. And so if we look at propane, what we'll see here is that propane is what's considered usually nonpolar, right? It is to have very tiny poles, but they're not really significant. You can see them right here, actually, in the blue and green. They're just very minor, okay? But what happens is, again, you have an instantaneous dipole that will develop. It's literally due to probability, because you have a probability of one electron being off the center and developing a charge, right? And so you develop a charge on one side here. It's going to pull the electrons if it's positive, repel if it's negative, right? That's going to cause those other electrons to develop a charge differential. They'll start matching each other for a short period of time, and they'll pull each other together, okay? And so you end up with opposite charge, partial charge is attracting, and you end up with this happening, millions of times a second in different spots, and just a slight amount of attraction, okay? If you have enough electrons and a long enough chain, you'll end up with a huge amount of attraction just from all these happening at once, okay? Think of them like strings versus the hydrogen bond being a rope, okay? So this is like little threads, much weaker individually, but you have, anybody ever seen Oliver's Travels? Or Gulliver's Travels, excuse me? Yeah? Aw, nobody else? That's disappointing again. He gets wrapped up by little people, like this tall, with string. Can't get up. Okay. You all have a great day. I'm a minute late. I will talk to you next time about the next part. We actually made really good time. My goodness. Uh-huh.
So, I was